Hello, this is Chuck Ridgway, Automation Technology Manager at Horner. Thanks for joining us for another Tuesday live stream. Well, it's good to be back live again. Last week we pre-recorded because we had our big North American sales meeting, which went great, by the way. It was good to see all my colleagues from around the country, and even the Canadian guys, Rod and Gord, who've sent their smoke our direction all the way to Indiana. But that's okay. We'll forgive you this time. Well, anyway, as I said before, it is good to be back live again this week, and here is our topic. Modbus variable conversion in Enhanced IEC. Now, the reason this is an important topic is because a lot of folks are taking a close look at programming Cscape using the IEC languages. And with Enhanced IEC, there are some implications when it comes to Modbus you should be aware of, and we're going to cover those with you today. Now, let's talk about some of the advantages of IEC and Enhanced IEC. And to do that, let's bring in our product manager, Mr. Casey Gardner. How are we doing today, Casey?
Hey, not too bad. How's it going, Chuck?
Going terrific. Now, a lot of people are looking at IEC these days. What are some of the advantages of IEC programming?
Sure. So one of the big ones is just overall flexibility in terms of language support. So we support the full IEC-61131 suite, which is up to 5 different languages that you can choose from to program in. So again, coming from whichever type of programming background you may have, that might be an advantage first and foremost.
Absolutely. And for those folks just fresh out of college, one of the languages available is structured text, which is more of a text-based programming language, which they may be used to with C and Python and some others.
Absolutely.
So, all right, so that's standard IEC or just IEC programming in general. At Horner, we also have something available in Cscape called Enhanced IEC. What's that all about?
Sure. So this is going to be an exclusive feature for the XL and XL Prime series. It is a licensed feature, so it is a one-time upgrade for per unit type of deal. That's a list price of around $50, so a fairly modest cost. But basically, it enables a suite of enhancements that we've added for the IEC 61131 languages. So one major thing is improved performance. So it's got faster overall scan time. It also has about 5 times or more of the overall variable space. So I think it's up to around 128K of overall variable space, which is really good. And a number of other enhancements. Do you want to mention a couple?
Yeah, I think one of the things I was thinking about that people should take advantage of is the simulation or the logic simulation that's available. So you can do logic simulation of your program without having any hardware. And then there's some advanced debugging tools, some breakpoint and tracepoint stuff that's available as well. So definitely worthwhile and definitely something people should look at.
Absolutely.
Okay, so while I'm covering the material today on the variable conversions, Casey will be standing by to answer any questions you might have for those of you watching live. Give us those questions in the chat section and Casey will get those answered right away. If you're watching this on replay, like a lot of you do, give us those comments and questions in the comment section and we'll reply to those in about a business day or so. We'd really love to see those comments. All right, let's take a look at how we're breaking down today's topic. Okay, we're going to start with a really quick Modbus review, just a single slide. We're going to talk about the traditional way that Modbus has been implemented in the Horner controllers. Then we're going to pivot to talk about standard IEC versus enhanced IEC and the way things are handled a little bit differently with those two approaches. And then we're going to get to the Modbus implementation for enhanced IEC. That's really what today's program is all about. How is it different than the other language options we have? And how does it impact specifically 32-bit variable types over Modbus? And of course, we'll have plenty of demonstrations. Okay, so let's do our quick one-slide Modbus review. Well, as most of you know, Modbus is by far the most common industrial protocol that people use when they need to link multiple devices from multiple manufacturers. Yes, there's plenty of other protocols out there, and there's some others that maybe we prefer. But when it comes to linking multiple manufacturer type devices, Modbus is king. Now there's 2 variations of Modbus that are the most common. From a serial standpoint or RS-45 standpoint, Modbus RTU is pretty much what's available out there most commonly. And from an Ethernet standpoint, Modbus TCP is by far the most common. Now, Modbus over a serial port is a master-slave type configuration, whereas Modbus over Ethernet is a client-server type architecture. Now, let's talk about how Modbus has its data modeled, which definitely comes into play for today's conversation. Okay, so Modbus was really designed around a traditional PLC, not a PLC of today, but a PLC of, say, 20 or 30 years ago, where all the data was either Boolean or integer-based, and you typically had digital inputs, digital outputs, analog inputs, and analog outputs, and the analog data was pretty much housed in 16-bit type variables. Now, Modbus was also based on an addressing scheme that was 1-bit based, as well as based on a 5-digit variable scheme with 10,000 different registers per variable type. So you could have a total of 40,000 registers. Now, there's also a 6-digit scheme, but that one is not nearly as common and doesn't really come into play for today's conversation. Now let's talk about how traditionally Horner has implemented Modbus in its product. So just like Modbus is based on a traditional PLC model with 16-bit registers and 1-bit Boolean type addresses, the original OCS was based on a similar architecture. Now, the address types are a little different. There's more different types of addresses, not just 4, but it was really quite easy to set up a variable map between Modbus data types and Horner data types. So that's really the way it's been accomplished over the years for just about all the different programming styles within the Horner controllers. So this standard map has really served everyone well. Now let's talk about some of the differences between standard IEC and enhanced IEC. Now, some of these were things that we talked about with Casey, but some of this is also just kind of deeper architecture type information. So with the standard runtime engine that's included with just about every OCS controller from the micro OCS on up, it supports variable-based advanced ladder, register-based advanced ladder, and standard IEC. All those languages can be executed from the standard Horner runtime logic engine. But as Casey mentioned, there's an additional option available for the XL series, XL Prime series, as well as the upcoming Canvas series, which allows enhanced IEC to be executed as well. That's because there's a special enhanced IEC runtime logic engine also included on those products. Now, if we take a look under the hood a little bit, here's what's happening. So with those 3 languages that are the originals, register-based advanced ladder, variable-based advanced ladder, and standard IEC, those all execute from the Horner runtime engine. But if you'll notice, the standard IEC requires a code conversion inside of Cscape before download. That's because as it is created, the standard IEC can't run directly on the Horner logic engine. It does need some code conversion, and that happens in the background in Cscape. But the enhanced IEC can run directly from the enhanced IEC runtime logic engine, which means since there's a more direct connection and there's no conversion required, that the execution times are faster and the capacity is larger. Now, one of the things, though, that happens with the enhanced IEC is that there is no underlying register base to enhanced IEC. So traditional registers for internal storage like R's, M's, and T's do not exist. Therefore, you can't use the standard memory map between Horner type and Modbus type to make the Modbus implementation work. Instead, what happens is in enhanced IEC, you create 4 different arrays for the 4 different types of Modbus data that's available. And that allows integer and Boolean data types to work really well, seamlessly, really. So in your configuration, for example, Modbus TCP, you go in and select that you want to configure Modbus server or Modbus slave as it's shown on the screen, and it gives you the opportunity to allocate 4 different arrays, one for holding registers, one for input registers, one for input bits, and one for coils. And you can set whatever size you want. And it's through those arrays, those arrayed variables, that Modbus data is exchanged with the outside. And again, For integer data and Boolean data, it just works seamlessly. However, what about non-integer data types? For years, manufacturers have been exchanging floating point data, double integer data, and more through Modbus, which is based on integer data. So how did that work? Well, with the 3 editors available from Horner, the register-based, the variable-based, as well as standard IEC, there was always that underlying register-based structure that you could lean on as a shortcut to easily concatenate 16-bit registers into real and floating point type and also double integer type data structures. That isn't available with Enhanced IEC, and also IEC also has a fairly strict variable type matching requirement, so you can't mix and match integer and real data with the same function blocks. That's not going to work either. So you have to take a different approach when it comes to Enhanced IEC. Now, hopefully I'm not scaring you too bad, because the solution is really quite simple. What we've done at Horner, like we often do, is we have created user-defined function blocks to make it really easy for you to take double integer variables or real variables and either split them into separate integers that can be sent over Modbus, or to take separate integers over Modbus and join them together to create double integers or floating points. So it's really just a fairly simple approach using these user-defined function blocks. Now, if you looked at the data or the programming, if you will, or the logic inside these user-defined function blocks, it's not as straightforward as you might think, but we've done all the heavy lifting for you. So really all you have to do is use these UDFBs. Now, the first 4 you see on the screen here are related to splitting and joining double integers, whether they're signed or unsigned. And then we've also got the same approach for floating point, for either joining or splitting. So they're really pretty straightforward. Now let's talk about a real world application. So let's say that we have a machine which is utilizing an encoder and has available over Modbus from, let's say, a SCADA package can monitor a current position of the encoder, whether it's for a machine, some sort of conveyor, or something else on the machine that needs to be monitored remotely. Well, with that 32-bit encoder, that is going to be stored locally in the OCS as a double integer. However, when it's going to be retrieved through Modbus by the SCADA package, Modbus really only supports single integers. So what are we going to be able to do there? Well, what we're going to do is we're going to use one of those user-defined function blocks so that we can split that double integer variable into separate integer components so that it can be seamlessly read by the SCADA package. Okay, so here's the steps that are going to be required. Of course, the first thing we're going to do is we're going to make sure that we've allocated those array type variables in our Modbus configuration. And because encoder position is really a read-only variable from a SCADA package standpoint, we're going to allocate the input register location as where that's going to be stored. And we're going to just randomly, or not randomly, but we're going to decide in our example that the first 2 input registers, Modbus 30001 and 30002, are going to be the addresses where the encoder position can be monitored, okay, or read. And in the OCS, after we've started with our double integer that has that 32-bit data, our user-defined function block is going to split that up into 2 16-bit variables that we're going to store in Modbus input reg 0 and Modbus input reg 1. So that'll be where we put them, the broken down data, so that it's accessible over Modbus. Okay, and then, again, in our program, it's really just a single function block where the input for that user-defined function block is the variable we want to split, which is our encoder position, which is a double integer signed variable. And the output of that UDFB is our 2 components, both integers, one that we're going to allocate to index 0 for Modbus input registers, and the other one we're going to allocate to index 1 for that same array. Again, pretty straightforward. Now, what about going the other direction? Maybe in the same application, the SCADA package is writing a set point, a position target, let's say, that we need to monitor in the OCS that's coming in over Modbus. And again, it's going to be written by the SCADA package into 2 separate integer locations. Now, this time, because it's being written to the OCS, it's going to be stored in holding registers instead of input registers. Input registers are read-only, holding registers are read-write. And again, we're going to allocate those to 40,001 and 40,002. So that means, again, that they're coming in through that input array, the distinct components, and then we're going to use the join UDFB to take those two different integers and combine them into a single double integer. All right, so that's really what we're looking at today. Let's go ahead and take a look at how we accomplish this on the bench, but we're going to start instead from Cscape to kind of review what's happening there. Here is my program, which is effectively doing exactly what I just talked about on the slides. Let's start from the configuration. So if we go into the hardware configuration and we go into the LAN 1 configuration and then to the Modbus slave configuration, here's where we see the 4 different arrays that we have allocated to Modbus data for holding registers, input registers, coils, and inputs. Now, these arrays were created and dimensioned using the variable window. And depending on the size of those arrays, Cscape will automatically allocate the size for each of those different Modbus data types. So we've only allocated 4 holding registers, 4 input registers, 4 coils, and 6 inputs. And that's based on the dimension of those arrays that we've created. And they could obviously be much larger than that, but that's what we've used for this example. Okay, so now that we've got that configured, those Modbus addresses configured, now we've got these 2 UDFBs that we're using. One of them is used to take our encoder position, which is a double integer, and split it into integer components that are mapped into Modbus input registers. The other one takes the 2 inputs that are being written by the SCADA package into the holding register area and combines those to create the target position. All right, let's take a look on the bench at how this looks from a demonstration standpoint. Okay, so let's take a look here at, first of all, the encoder position. So the encoder position obviously is representing the position of the encoder, and that is a double integer value. And I'm making this just editable, if you will, from the screen, okay, for demonstration purposes. And then our UDFB that splits those into 2 different components at addresses 30,001 and 30,002, where they can be read by the SCADA package and then reassembled on the other side. So to simulate our SCADA package, I'm using Modbus poll. So let's go back to my computer, and this time let's bring to the forefront Modbus poll. Okay, so let's take a look here. We've set our encoder position at 67,000, and it's being displayed here, as you can see in Modbus poll. And if I change that on the screen, I'm going to change that to 69,000. We should see that change here on the screen as well. Yep, you just saw that corresponding change. Okay, so as you can see, we have successfully configured Modbus poll to interpret the data that we're sending over Modbus, which is really integer data, but to interpret it as a double integer value instead. Okay, and then going back the other direction, we have target position. So let's take a look at the target position. That's coming in as 2 separate integers, and then we're reassembling it here. So we've assembled it as 660,000. If we go back and take a look at how it's being sent from the SCADA simulation, we can see that, sure enough, 660,000. And as we modify it here, let's say to 665,000 and hit send, okay, and then head back to our bench, we can say that we successfully assembled that data properly. So by using these really simple user-defined function blocks, we've been able to take something which otherwise could be a little bit of a pain and make it pretty straightforward. If you took a look at the logic inside these UDFBs, it's not quite as straightforward as you could imagine. And of course, the floating point one especially, which I haven't demonstrated yet because that one requires some heavy lifting to be sure, but not on the user side, because when you use a UDFB, everything works just seamlessly and very easily. Okay, so that's what we wanted to cover today, really showing you how to utilize these new UDFBs to support whatever data types you need over Modbus, even with Enhanced IEC. Okay, this is just a little supplemental video because I forgot to demonstrate one thing during today's live stream, and that is how do you import user-defined function blocks into Enhanced IEC? Now, it's really the same way that we do it in Advanced Ladder, variable-based Advanced Ladder, but I thought I would distinctly show you for Enhanced IEC. So what we do is we go over here in the Project Navigator. Under Logic Modules, we right-click and say Import Logic Module. And then we navigate to the folder that contains the user-defined function block files. Now, one thing that is a little different, and that is the file extension for IEC, user-defined function blocks, is XK5, whereas the file extension for variable-based advanced ladder is CPU. So that is a difference. But effectively, once you have found the UDFB that you want to import, you simply select the file, hit open, and then it will be added under UDFB modules over here in the Project Navigator. Now, once it's imported into your project, it's very simple to add it to your logic. You go to the section of logic where you want to add it, and then you go over to the project toolbox, and at the very bottom under project, you'll find when you expand that, all of the user-defined function blocks that have been added for that project. So the one that we just added, join UDINT, can be added to my project simply by dragging it off to the location in my logic where I want to add it. And like all user-defined function blocks, they do need naming because they're each a unique instance of the other. So that is very important, of course, because it allows you to have multiple of the same UDFB just working on different variables and different Modbus data in your program. Okay, so that's how you add a UDFB to your project in Enhanced IEC. Okay, so here's our wrap up today. Again, Modbus is a register-based protocol used everywhere in industry. Its native data types are 16-bit integers and 1-bit Booleans, even though there's plenty of other data, whether it's double integer or floating point, that needs to get transmitted over that protocol. Now, for most of the Horner languages, register-based ladder, variable-based ladder, and standard IEC, the OCS can utilize its built-in %R memory to very easily concatenate integer values into those 32-bit data types. But Enhanced IEC does not have that underlying structure and therefore requires some extra work. In this case, some simple UDFBs we've created to make splitting and joining the data types as easy as possible. Okay, so this is the part of the program where I remind you we're here every Tuesday at 2 o'clock, whether it's fully live today or pre-recorded like last week. But in any case, we're always streaming our videos live on Tuesdays at 2 o'clock, and somebody's always standing by to answer your questions. Last week, it was Nate Beachy who was standing by. Thanks for that, Nate, for answering those questions last week. Okay, now this year we are celebrating our 10th year of Horner Lighting products, so don't miss the great Horner Lighting content on our YouTube channel alongside our great automation content. Okay, upcoming training opportunities. Well, the basic training for next month is full. If you were planning on coming to that trip, I'm hoping you're already signed up. Otherwise, you'll have to wait until later in the year for basic training. But the good news is there are still seats available for advanced OCS training in August. So go to our website and get signed up for that. Now, I'm really excited about next week. So next week, finally, we're going to be doing a really deep demonstration of Cscape 10. Now, for those of you who aren't in the U.S., you may not realize that next Tuesday is a national holiday here in the U.S. It's our July 4th Independence Day. So because of that, we're going to do our Tuesday live stream on Wednesday instead, but it's a big one. We're going to be celebrating not only Independence Day, but celebrating a real preview of Cscape 10. So we're getting really close within just a few weeks from the customer beta starting for Cscape 10. But this is really the first public look, the first full demonstration of Cscape 10 that we're going to be doing on our live stream Wednesday next week instead of Tuesday because of the holiday. Okay, if you haven't subscribed to our channel, don't hesitate. It doesn't cost anything. And if you choose notifications when you subscribe, you'll be notified every time we go live or every time we post a new video. Okay, so until next week, the day after Independence Day, the day after July 4th, when we give you a big preview of Cscape 10, let's all get out there and do us some good.